Welcome to another lecture on linear programming. We have looked at linear programming from multiple perspectives. We have looked at convexity theory, we have looked at duality theory, and we saw some applications of duality theory, right? From now on, we will keep seeing more and more applications of linear programming in diverse areas. The first area we are going to cover is network flows, and probably you might have seen such algorithms in the algorithm course, right? So we already saw one example in the exam where we talked about matching and covering, right? So matching and covering, connectivity, you might have heard of maximum flow problem, is that correct? Right? So these are examples of network flow problems, fall under network flow problems, and were kind of standard problems for which people came up with nice algorithms. And some of the things which we will do might be familiar to you, but we will look at them from the perspective of linear programming. That's what we want to do. Okay, so just by show of hands, how many people know what max flow problem is? So good. So it seems that most of you are familiar with what max flow problem is. That makes my problem easy. The idea is that you are given a graph. This is going to be our notation. Vertices, E is edges, and in this case, the graph is directed or undirected? Directed, right? In this case, it's a directed graph, right? And probably before we start explaining this problem in mathematical detail, let's just say why it is a max flow problem, right? It has a very nice real life application to it, which appears in many situations, right? And what is the situation? Let's say you have some source of water, and there is some city where the water is needed, right? And then you might have different connections of pipes which might take you to these places, right? Let's say this is where, you know, the water can be pumped in these directions or something. And obviously, each of these pipes have a diameter, right? And we can say that the diameter, so I should say that the edges correspond to pipes, and I can say that diameter correspond to some kind of capacity, right? So we can send 3 liters of water per minute or whatever. So we have these capacities, and then the idea is that how much water can you send from this source to this city, right? So correct. So what we remember is, now if you want to abstract it out mathematically, we are given a graph which has vertices and edges. The edges are directed. We are in a directed graph domain, and then each of the edge is given some capacity, right? So if this is an edge between u and v, then I'm saying that it has capacity uv. Edge right? This could be water, this could be oil, this could be blood, there could be, from heart to some organ or something. We can ask, in many situations, we can ask how much of the flow of some liquid, something, some material can go from the source to the sink, right? This is the abstract problem which we want to solve. And as mentioned before, you have seen it before, we will see that linear programming gives us very nice interpretation of the results known here and gives us nice algorithms. Okay. So, coming back to the description, the problem will be specified by the graph, that means vertices and edges, capacities, and then for our case, for simplicity, we will assume there is single source called S and single sink called T. Okay. The task is to maximize ST flow. Make sense? This is what we want to do. Okay. What are the constraints here in English? Sorry? Right. So I can't put more flow than a capacity. So what should be my variables, right? Or let's just write constraints first, and then we can write mathematically these constraints. So first thing is flow through each pipe should be less than, okay, less than, since I'm sure one of you will point it out, so less than or equal to capacity of that pipe. Correct? Anything else I have to keep in mind? Sorry? Right. So I don't want water to be lost at any of these vertices, right? That means for each vertex, the amount of flow coming in should be equal to amount of flow going out. Okay, and then okay, so this is the quantity which we want to maximize, right? This is the flow conservation constraint, and this is capacity constraint. Correct? Good. Great. So this is the English description of the problem, and it's not hard to convert into the mathematical description, right? We just need the variables FUV, right? What does FUV denote? Flow from U to V. Right? Then what is my first constraint saying? Correct? What is the second constraint saying? How can I write the second constraint? Why don't you write down in pen and paper the constraint? So amount of flow going into a vertex, let's say I pick a vertex V, so amount of flow going in correct? So this is saying look at all the pipes which are look at all the pipes which are going towards V. Let's say their starting point is U, so look at all U's such that there is a pipe going from U to V. Look at the flows there. This is the amount of flow coming into V. So if this was V, then how many edges are coming into it? S V1, V4. So if I want to write down the equation for V, I am going to sum up the flows from S to V and V1 to V. This should be equal to the amount of flows going out of V to V3 and V to V4, because no water can stay here. Correct? This is the equation. And how do I write the third equation? Summation over U such that this is the amount of flow going out of S. This is the amount of flow going into T. Okay. So I will keep this picture because this is kind of instructive. So the first thing to remember is that we really don't need the third constraint. So since Dev is nodding his head vigorously, anyone else except Dev will tell me why? Exactly. Since the flow is already conserved, then we know if at everywhere there is no flow leaving in or out, then if I am pushing 10 units of water, it can't stay anywhere else, so it has to go to the sink. So it is just part of the second constraint in some sense. So I will not put it explicitly. So then this problem, if I want to write it, this is the amount of flow, correct? This is what I want to maximize. Since this constrained it out, the problem straightforward become this. This is the quantity which you want to maximize such that it follows the flow conservation, it follows the capacity constraints, and each flow obviously has to be positive. There is a direction associated with it, so the flow should be positive here, right? And why are we happy? Exactly. We are very happy because this is a linear program, correct? And just once more, this is a linear program where the parameters or the input would be the graph and the capacities, and the variable is UV. And actually in the input you also have to specify which one is your source, which one is your sink, correct? So once you are given all those descriptions, you can make this linear program, correct? And just to make sure that we are on the same page, how many constraints are there? How many variables are there? Number of edges, right? And how many how many constraints are there? Right. So number of edges plus number of vertices minus 2, correct? And now since it kind of seems weird that we don't have flow constraints for 2, it feels like a non-uniform kind of a problem, right? So there is a small standard trick to make this uniform. Okay, what is that trick? Exactly. We create an edge from T to S, okay? And we can say that we want to maximize FTS. So whatever is the flow from S to T, we are saying it goes back, then we have flow conservation everywhere, right? And what capacity should I give it? At this point I don't know it, right? So let's say infinity. Let's start with infinity. So then notice that now I have an extra edge. This contains T comma S also, okay? Okay, sounds good. Do you agree that these are equivalent programs? I see that there is some slight unease, right? Because yes, they are equivalent programs, but then you are going to have a constraint here which says, is this allowed in linear programming? Is this not allowed in linear programming? Yes, no? Are you happy with it? Can I leave it? Can I put it in linear programming solvers? Why can't I put it in the linear programming solver? Infinity is not a number, right? So what is the small fix? Right, exactly, very nice. I can replace it infinity by a very big number, right? For example, just sum up all the capacities. Definitely that's an upper bound on my flow, right? So replace by a suitable upper bound, okay? And then you are not worried about, actually putting this thing as a linear program, right? Okay, and then this makes sense. Sorry? Why are we putting this constraint?
We can just say it's non-negative.
Okay, sure, that is also fine. So, if you are not happy with an upper bound, if you just think deeper, then you realize that you can skip less than infinity constraint. Okay, but then someone says that, oh, it doesn't uniform. You know, for there is one edge, so sorry, be CT, yes, CTS. I want to keep it as infinity. Yes. No, the constraint is this, right? The FTS less than CTS is the constraint, and I wanted to put infinity for CTS, right? So this constraint I will avoid, right? This constraint I will avoid, right? Great. So this was the maximum flow problem, and there was an LP for it.